Hello everyone. My name is Algener Bikandao and I'll be your reporter for today. So I'll be tackling about flow routing techniques, which is the Muskingum method and the Reservoir method. So before we proceed, let me define first what is a flow routing. So flow routing in hydrology is a technique used to predict the changes in shape of a hydrograph as water moves through a river or a reservoir. Flow routing is also called flood routing since it's widely used in flood estimations. The hydraulic analysis of problems such as flood forecasting, flood protection, reservoir design, and spillway design invariably include flood routing. In the said applications, two broad categories of routing can be recognized. These are reservoir routing and channel routing. So a variety of routing methods are available and they can be broadly classified into two categories. And these are hydrologic routing and hydraulic routing. Why flow routing is important? So in flood forecasting, hydrologists may want to know how a short burst of intense rain in an area upstream of a city will change as it reaches the city. Routing can be used to determine whether the pulse of rain reaches the city as a deluge or a trickle. So routing can be used to predict the hydrograph shape and thus lowland flooding potential subsequent to multiple rainfall events in different subcatchments of the watershed. So, flow routing analysis. Flow routing analysis is a procedure to determine the flow hydrograph at a point on a watershed from known hydrograph upstream. So, in the picture, you can see an upstream hydrograph and downstream hydrograph. So, since if you'll notice the elevations in both curves from upstream and downstream is not the same. So the elevation in inflow is much higher than the outflow. So from inflow, it passes through function or the transfer function, then the peak or the elevation of the curve decreases. So in the second picture, you can see the definitions of some terms or definitions in hydrograph. So you can see the lag, the peak flow attenuation. So that's between the peak of the outflow curve and the inflow curve. So attenuation. So from the picture earlier, so the peak of outflow hydrograph will be smaller than of the inflow hydrograph since this reduction in peak value is called attenuation. So next is the time lag, or the lag in the previous picture. So the peak of the outflow occurs after the peak of the inflow. The difference between two peaks is known as lag. Then the attenuation and lag of a flood hydrograph at a reservoir are two very important aspects of a reservoir operating under flood control criteria. Next is we have the types of flow routing. So as I've said earlier, there are many ways of routing methods. So those are classified into two categories. So this is the hydraulic routing or the distributed flow routing and the hydrologic routing or the lump flow routing. So first is the hydraulic routing or the distributed flow routing. So hydraulic routing uses both continuity equation and momentum equations such as equation of motion. It calculates the flow as a function of both time and space. Compared to hydraulic routing, it is more complex but produces more accurate results. Um, the flow rate and the water level are solved simultaneously. Equations used in this routing results from a conservation of momentum, assuming the uniform velocity distribution or the depth average, hydrostatic pressure, and small bottom slope. In hydraulic routing, it is intended that the dynamics of the water or flood wave movement be more accurately described. So next is the hydrologic routing or the lump flow routing. So hydrologic routing uses continuity equation to relate the known inflow hydrograph with the unknown storage and discharge using either linear or curvilinear relation. It calculates the flow as a function of time only. So unlike hydraulic, which calculates the flow as a function of time and space, hydrologic routing calculates the flow as a function of time only. It is relatively simple with satisfactory results, and the flow rate is solved at the desired location, then the corresponding water level computed assuming steady non-uniform flow along the channel. Next is we have the basic equations. So the equation of continuity in all hydraulic routing as the primary equation states that difference between the inflow and outflow rate is equal to the rate of change of storage. So we have the I or the inflow um, minus the Q or the outflow rate is equals to ds all over dt or the change of storage. Alternatively, in a small time interval delta t, the difference between the total inflow volume and the total outflow volume in a reach is equals to the change in storage in that reach. So we have the um, average inflow in time delta t minus the average outflow in time delta t is equals to delta s or change in storage. By taking the average inflow and the average outflow and the delta s or change in storage with suffixes 1 and 2 to denote the beginning and the end of the time interval delta t, we get this equation. So this one. So the time interval should be sufficiently short so that the inflow and outflow hydrographs can be assumed to be straight in that time interval. So the hydraulic models needs to estimate hydraulic parameters using recorded data in both upstream and downstream sections of rivers and or by applying robust optimization techniques to solve the one-dimensional conservation of mass and storage continuity equation. So first is we have the Muskingum method. So in a very long channels, the entire flood wave also travels as a considerable distance, resulting in time retribution and time translation as well. Thus, in a river, the distribution due to storage effects modifies the shape, while the translation changes in position in time. So in reservoir, the storage is a unique function of outflow discharge. Storage in the channel is a function of both outflow and inflow discharges, and hence a different routing method is needed. The water surface in a channel reach is not only parallel to the channel bottom but also varies with the time and time. The total volume in the storage for a channel reach having a flood wave can be considered as storage or prism storage plus wedge storage. Uh, Prism storage. The volume that would exist if only the if only flow occurred at the downstream depth. The volume form can be imaginary plane parallel to the channel bottom drawn at the outflow section water surface. So we can see at the bottom is the um, prism storage, and at the top is the wedge storage. So storage is divided into two. Also we have the inflow minus Q and the Q at the bottom side. Um, Next is the wedge storage. So it is the wedge-like volume formed between the actual water surface profile at the top of the surface of the prism storage. So at a fixed depth at a downstream section of a river reach, the prism storage is constant while the wedge storage changes from a positive value at an advancing flood to a negative value during a receding flood. So pag magbaha man is ang flow niya is dili man na siya constant sa taas. So ang mura gina-consider lang ana na constant is katong prism storage sa ilalom. Then kanang wedge storage is mao na siya kanang sa taas niya na murag kanang dili constant, kanang murag naga wavy siya na flow. So mao na siya. So at a fixed depth at a downstream section of a river reach, the prism storage is constant. So mao na tong giingon ako ganiya na constant tong prism storage, while the wedge storage changes from a positive value for advancing flood to a negative value during the receding flood. So total storage in the channel reach can be expressed as S is equals to K times X um, I raised to M plus 1 minus X times Q raised to X. So by the way, ang K ug ang X dira is mao na sila ang mga Muskingum coefficients. So where K and X are coefficients, so mao na sila Muskingum coefficients. And M is equals to A constant exponent. It has been found that M varies from 0.6 for rectangular channels to a value of about 1.04 natural channels. So assuming that the cross-sectional area of the flowed section is directly proportional to the river or to the discharge at the section, the volume of prism storage is equals to KQ, where K is a proportionality coefficient, and the storage volume wedge is equals to Kx times I minus Q, where X is a weighing factor having the range of 0 less than X less than 0.5. So the total storage is therefore the sum of two components. So S is equals to K um, Q plus Kx times I minus Q. So it is known as Muskingum storage equation, representing the linear model for routing flow in streams. So mao ni siyang summary sa mga coefficients and mga factors needed for solving Muskingum method, for solving using Muskingum method. So naatay S Sem KQ S wedge equals to Kx. We also have I minus Q times K. Yan, natay weighing factor na mag-vary sa 0, less than x, less than 0.5. We also have x value which is 0.0 to 0.3 for natural streams. So, kani siya, mo ni siya ang storage kaning naa sa picture. So, ang itaas ana is mauna siya ang sa wedge. Anya sa ilalom is ang constant. Mauna siya ang sa prism. So, next, we have the Muskingum's routing equation. So, we have the O sub j plus 1 is equals to C sub 1 I j plus 1 C plus C sub 2 I sub j plus C sub 3 O sub j. Then we can calculate the C1, C2, and C3 by this equation. Also, C1, C2, and C3, if you add them, the answer should be 1. For the best results, the routing interval at delta t should be so chosen that k greater than delta t greater than 2kx. If delta t is less than 2kx, then the coefficient C1 will be negative. So generally, negative values of coefficients are avoided by choosing appropriate values of delta t. So to use Muskingum equation, to route a given inflow hydrograph through a channel reach, K, X, and O should be known. So these are the procedure. So first, knowing K and X, select an appropriate value of T. Then 2 is calculate C1, C2, and C3. Then 3, starting from the initial conditions known inflow-outflow, calculate the outflow for the next time steps. Then lastly, repeat the calculations for the entire inflow hydrograph. So, example para sa masking method. So, kani siya nga example is gikan lang ni siya sa atuang sim. So, the inflow and outflow hydrographs for a reach of a river are given below. So, natay data sa time, then inflow, then outflow. So, determine the value of Muskingum coefficients K and X. So, kani siya is na-tabulate na siya daan. So, giyon sa man na siya pagkuha. So sa man na siya pagkuha. Kanang kaning sa main storage is naatay 2. Giyon sa man na pagkuha ng value dira sa first row na 2. So, naatay 39 o 35 na inflow o outflow. So, ang gamiton natin na formula na is kani. So, naatay I1 plus I2. Wala man tayo I2 o O2. Ato ang data pa lang dito sa first row is I1 pa lang na tanan. Then O1. So, at gamit i-substitute lang nato na siya dito na formula. So, atong inflow natay 35 all over 2. Nga naata interval na T, which is ang routing period na T na 1 day. So, minus na to siya diri. Minus sa outflow. So, atong outflow dito sa graph is ang O sub 1 na to is 39. So, wala pa tayo O sub 2. Divided by 2 times interval na 1. So, makuha na to ana is negative 2. So diri sa second row na to, so maapil na ang data diri solve karon sa first row. So ang I1 na to is kaning second row, then naa na tay I2 na first row. So gamiton lang gyapon nato ning formula. So I1 natay I1 na 125 plus I2 na 35. Kanya divided by 2 times gyapon nato siya sa time interval na t. So natay 1 day minus outflow. Unsa man ang outflow? 52 ang O sub 1, 39 ang O sub 2. Divided by 2 na to times 1 day na interval. So makuha na to ana is 34.5 kung i-calculate. Karon nganong 34 laman siya dire? Since ato ang unit man is cubic day, so dili ta pwede mag 34.5. So kuan 34 ta, whole number lang ta tanan. So same process lang siya hantod sa ilalom. So dire naman sa cumulative storage, first row nato is as is lang na. So naa siya pattern or naa siya formula sa pagkuha aning cumulative storage. So kani from dire na row 1 na cumulative storage, i-plus lang nimo na siya sa mean storage ng row 2. So 34 plus negative 2. So makuha na to ang 32. So dire na pud sa row 2, plus nimo siya sa 180, 32 plus 180. So makuha na to ang 212. So same process lang gyapon na hantod sa ilalom. So mao na siya ang para dire. Karon proceed na pud ta sa X. So unsaon man nato pagkuha ng X? Giunsa man ni pagkuha ni mga datas dire. So atong gamiton ani nga formula is kaning X times I plus 1 minus X times O. So by the way, atong X na gamiton is X is equals to 0.2, X is equals to 0.25, then X equals to 0.3. Diba kay giingon kanina na ang X daw sa natural stream is between sa 0.0 hangtod sa 0.3. So mao na ni siya. So para ni siya sa number of trials nato kani. So mao magud ni ang gamiton nato ng mga datas para sa atuang hydrograph. So giun sa asa magikan ning 0.2 I nga 0.80, dire gyapon ni siya gikan. So kani 0.2 kani 0.2 mao man ning X. Para ni diri na roll sa 0.2. Kani times I. So mao na ning XI. So plus kani diri siya nakatotal mo gani diri. So meaning i-plus gyapon nimo tong 0.2i plus 0.80. So wala ni siya ang total diri. So parehas lang gyapon sa diri. Kaning 1 minus x. So 0.8 ni siya kay 1 minus 0.2. So 0.8 kana times O. So mao na kanilang ang gamitan na formula, then makuha na nimo ning tanang values diri. So kaning 0.2, 0.25, 0.3 same lang ang process ana tanan. So after nimo makuha tong values dito sa table lahat, so i-graph na na siya. So, di ba naaman tulo ka row dito. So, naatay x na 0.2, x 0.3, x 0.25. So, diri na nato. Pag human graph ani, diri na nato ma-determine kung asa si k. So, ma-determine nato si k kay k is determined by measuring the slope of the median straight line. So, straight line siya is found to be 0.7 days. So, sa tulo ka graph, so, pansin nyo, hiwi nin duwa 0.3 ug 0.2. So, nag-straight lang siya sa median sa 0.25 lang. So, kani. So, diri lang siya may straight line. So, meaning, ang k na to is naa diri na graph. So, karon makuha na nato si k. So, makuha nato si k. Ya, ang answer po is kani siya na graph. X equals to 0.25 and k is equals to 0.7. So, mao na ni siya. So, next example, kuan gyapon na siya, gikan gyapon sa sim. So, the inflow hydrograph readings from a stream which are given below, for which the Muskingum coefficients of k is equals to 36 and x equals to 0.15. So, naa na tayo coefficients daan sa Muskingum na k o x given. Apply root the flood through a reach and determine the outflow hydrograph. Also determine the reduction peak and the time of peak outflow. So, kani na mo ni siya ang banggit na hydrograph reading. So, natay inflow, then outflow. Then, naka-QMEC gyapon atong inflow, kinaka-day, manggod na, naka-day atong ano. So, again, naatay time interval na sad. So, 0, 12, 24, 36. So, naatay 12 hours na time interval. So, at yes, 12 hours na time interval. So, kanina is 24 is equals to 1 day. So, since to nga sa 24, 12 is 1 half day. So, basically 0.5 na siya. So, natay x pod o k. So, kanidri na nato magamit tong C0, C1, and C2. Or C1, C2, C3. Parehas na. So, i-kuan lang nato siya. I-substitute. So, natay kx. Natay value sa k, natay value sa x. Then, 0.5 times t. Kana. So, i-substitute lang nato na tanan. Then, dapat, if i-plus nato ning tulo na gikuha nato C1, C2, C3 or C0, C1, C2, ang kwanjo dapat niya, ang answer is 1. So, 1 dapat siya. So, kung tingala mo, asagikan ang 0.15 diri o ang 0.5. So, ang 0.15, mauna ni siya ang day na to. Ano, mauna siya ang x na to. Then, ang 1.5, mauna na ang days sa k. 36 hours na k, convert siya sa days. So, 1.5. Then, ang t na to, is ang time interval. So, natay 12 hours. So, convert na to siya sa day. Is 0.5 or 1 half. So, para maka-graph ta sa atong hydrograph, so, kinahanglan nato ni siya na data. Since okay naman tong dire, na 1 na siya, so, pwede na ta mag-proceed. So, ang given lang dire by the way, isang time and ang inflow. So, para makuha ni mga datas, is makuha na to na siya gamit kani nga formula. So kani as is ning diri sa first, so outflow lang makuha na. Then sugod ta sa second row, so giun sa man pagkuha ning 0.90. So based diri na formula, so natay 0.02 times na to siya sa I1 ay sa I2 na to. So asa man ang I2 na to, kaning 45. So times 45, so mo na siya 0.9 or 0.90. So diri daw 0.31 times I1. Asa man ang I1 na to, dili kaning 45. Ang I1 na to is kaning 42. Kaysa I2 maning 45. So times 42. Kuha na to ang 13. Kuha na to ning 13. Karon kanina pod asa gikan ni 28.2. So natay formula diri na 0.67 times 01. So asa man ang 01 na to? 01 na to is kani outflow 1 na 42. So makuha na to ang 28. So same lang ang process ana antod sa ilalom. So ingana na siya pag solve. So gamita lang jud yung formula. Then para ning outflow, so kanilang gyapon. So plus lang nato ning tulo. So 28.2 plus 13.0 plus 0.9. So makuha nato ning 41.1. So i-plus lang nato ning tulo. So karon kung graph na siya is mao ni siya ang nawong. So ang gipangita sa problem kanina is ang reduction peak and peak outflow. So makuha na to na siya pag i-graph. So natay 108 qmec na reduction peak which is kani and naatay 84 hours na peak outflow. So dire. So mao na siya. So next is we have the reservoir routing. Reservoir routing considers modulation effects on a flood wave when it passes through a water reservoir. Through a water reservoir results in a flow hydrograph with attenuated peaks and enlarged time bases. Variations in reservoir elevation and outflow can be predicted with the time when relationships between elevation and volume are known. So these are the basic reservoir routing equations. So from continuity equation gihapon, so i-write lang siya as I sub t minus 1 plus I sub t all over 2 minus O sub t minus 1 plus O sub t all over 2 is equals to S sub t minus S sub t minus 1 all over delta time. So we have the inflow at times t minus 1 and t respectively. So we also have the outflow at t minus 1 and t, then storage at t minus 1 at t. So for reservoir routing, so the following datas have to be known. So first is the storage volume versus elevation for the reservoir. Second is water surface elevation versus outflow, and hence storage versus outflow discharge. So sa graph na siya makuha tanan. Then inflow hydrograph. So we have the I is equals to I times T, and the initial value of S, I and Q at time 0. So as horizontal water surface is assumed in the reservoir, the storage routing is also known as level routing. So that ends my report. Hope namin na tunan, then mawalan to siya. Thank you and have a good day po.